Hello ladies and gentlemen, and welcome to the Long Range Machine Control Mission Control Center. So here we've got everything set up with two modules talking to each other via the LoRa protocol. It's all working very nicely, just got this working this morning. So let's have a look and see what's going on. So right, we've got the two main modules here. This is the transmitter, and that's sending correction data, GPS correction data, to the dog, which would be a machine out in the wilderness. So we've got an interesting naming protocol here. I don't use base or anything like that because those words can be really confusing. So anything in mission control is named nest, like a nest of spiders or something like that, and anything that moves around is named dog. And you can have various types of dog, and you can have various parts of the dog as well, like its tail, snout, belly, and feet, and such like. So in mission control, which is called the nest, we've got various screens set up. This one, I think, that one represents the Raspberry Pi, the master Raspberry Pi on the nest. This screen represents the master Raspberry Pi on the dog. And this screen, which is quite interesting, this is the results of our... Oh, did you hear that? That little beep there, that indicated an error in the data. So we're checking the error as it comes through. So if there's a mismatch in the message number between this system and that system, it sounds a little alarm, which is quite nice. So yeah, getting back to here, this is a program called U-Center. So this is monitoring the GPS unit on the dog, which is, where is it? There it is, on the top of this Raspberry Pi there. That little square box right in the middle of the frame is the U-Block ZF9P, which is capable of extremely high accuracy, plus or minus 10 millimeters in my experience anyway. So looking at this, we can see all the satellites here on the right hand side buzzing across the sky. You get a really nice little map representation of all the satellites. This system's picking up GPS, which is the USA version of satellite positioning systems. Then you've got the Russian ones, GLONASS. Then you've got Chinese, which is Beidou, and European Galileo. I think there's a couple of others, but I'm not picking those up at the moment. And here, which is quite interesting, is a deviation map, and the accuracy is so good. Actually, let's zoom in on it a little bit more. I can hardly see any deviation at all. It's set to 3 meters, so let's just set this to 1 meter. Even at 1 meter, it's just like a blue blip there in the middle, moving around, which indicates, yeah, we've got an accuracy of 10 millimeters at the moment. Yeah, and this screen here, the blue letters, oh, another error there, indicate whether the correction data is working or not. So yeah, we've got a 2D fix, and I don't know if you can see that. There's our 2D accuracy in meters, which is like 0.01 meters. Oh, it's gone up to 0.02. Oh dear. Right. Right, just to prove that this isn't just like rigged up, what I'm going to do is kind of pull out the cable to the Arduino microcontroller. So this will destroy all the data that's coming through to the GPS module here. So let's pull that out and then see what happens on our screen. Here we are. So it's still fixed at the moment. It should go wonky fairly soon. There it goes. It has lost the fix. See now the GPS, the data goes all over the place. So it's probably worth just like zooming out a little bit here. Just see it properly. There we are. This is to 10 meters now. So the accuracy's dramatically affected. It's gone to 6 meters on the deviation chart there. So this is great. All systems are working. So this little LED here that represents the data being transmitted. If I can see it there. So every time it flashes, that's a data transmission. So it's going quite fast. So each packet is being transmitted at, it's going pretty fast. It takes about 5 seconds to send all the data across, which is pretty good. It'd be nice if it could be improved to 1 second, but I think that's a bit optimistic. So what I might do, so we've got 2 radio modules here side by side. One's supposed to be for transmit and receive. The one on the left hand side's not been used at the moment. What we could do is line up a whole load of radio modules on this board and separate them in terms of bandwidth by 500 kilohertz, and there's plenty of room on the 433 megahertz spectrum to have about 10 of them, I reckon. So that would be 5 megahertz either side of 433, which would be really nice. I think that would work quite well. And rather than using the Mega 2560, which are really great because they're so easy to work with. So when you're doing development work like this, quite often the microprocessors themselves can have problems, especially with the USB chips. So that's been great to work with, but they're quite bulky, and it's very difficult to get small ones with the Mega 2560 chips on. I have checked that I can use an ESP32 on ROS, and I actually got that working a while back. So what I might do is get a load of these, and they take up a lot less space. They should all connect into the Raspberry Pi on a USB hub, and I have 10 of them side by side, and you get a little LED display as well for nothing. So that might be something to do in the future. Who knows? I'll see how I feel in the morning.